Today I will be talking about also some kind of task queue, but more aims to scientific computations. My talk is about some tools that I have been working on with Olivier for the past year and a half, and I hope you will find it interesting. So the aim of the talk is to present you some tools to do some embarrassingly parallel computation in Python. And what I mean by embarrassingly parallel computation is that you have a set of tasks that are totally independent from one another, and that you would like to run in parallel, so it will be faster to run. And the traditional way to do that is to use a pool of worker when you enqueue all your tasks, and the pool of worker will take from the queue the tasks that you want to run and run it in separate thread, and then return the results. Return the results, and you can after that enqueue more tasks. And in the standard Python API, in the standard Python library, you have you have two options actually to do that. So first, and the oldest one was the multiprocessing pool, which was the first implementation. And I won't talk too much about this tool today because we find it a bit more faulty to less robust to faulty user code. And today I will talk more about the second API, which was introduced in Python 3.4, which is called concurrent.futures, which is basically a re-implementation of the multiprocessing pool, which use the multiprocessing primitives under the hood to give a more robust and safer implementation of the pool of workers. And I will also talk a bit in the end of this talk about loky, which is the tools that we have been developing with Olivier, which is some kind of a robustification of the concurrent future with some improvement in the API, but using the same framework than concurrent future. So first, I will start by giving you some overview of the concurrent future API, which is a bit less known than the multiprocessing one. So let's say that you have a function called fit models that take as an input like parameters, and that run heavy computation and return to you a model. And you would like to run this computation asynchronously, so you want to run it for multiple different parameters and get the results, and you would like to run this function for each set of parameters asynchronously. So what you would do with a concurrent future is use another executor object, which will abstract the pool of worker. So I'm here declaring instantiating an executor using thread workers. I will get back a bit later about should we choose threads or process. The API is exactly the same using concurrent future if you want to use thread or workers. So here I'm using 4 threads, and then what I can do is I can submit a job. So I'm just giving the function that I want to run in my thread and the parameter that I want to use, and this submit function will return almost almost immediately, giving you a future object. And this future object is an object that will hold the state of your computation, and that will be able to query to know a bit when the object is done. And after that, you can asynchronously submit other jobs. So for instance, a future second set of parameters with the same functions, or run other computation in your main program. And while you're doing that, the first fit model with parameter 1 is already running in the first thread. And then when you actually want to get back the results, you can call you can call result on the future 1 object or future 2 object that will block your main program until the computation is done in this thread. If the computation were already done, you will return immediately. You also have timeouts arguments, so you get back if the computation takes too long, then you can handle cleaner. You can avoid blocking your whole program. And when you get out of the with block, what is actually happening is that the executor is shut down and the resources are cleaned up, and you have a nice system with the results that run in parallel. You can also, there is also in this API, you can also use the map method on the executor that allows you to pass a function and a list of parameters, and all the computation will be run asynchronously. So it's basically doing, if you take a fit models and just a list with param 1 and param 2, you will have the list model 1 from model and model 2 in the results once the results are computed. So the future object is something which is interesting because you are able to know what is the state of your computation just by querying this object, and you can do some scheduling and you can know a bit more about that. And it's interesting to know that this object exists and that you can do some clever computation if you use it, but it's usually hidden in the pool of workers. So let's see a bit more what is happening internally when we run the code with the API. So basically, when you define your function, you're just defining the function in your main program. Then when you instantiate your executor, what is happening is that under the hood you are spanning 4 workers. So worker are threads, but could be also process, as we will see. And then when you're submitting your first job, the job, you have no way to decide which worker will be processing this job, but one of the worker will be processing it. So you're sending all the information you need to the worker so he can do the computations. Then when you're submitting your second job, as I said earlier, the first function with parameter 1 is already running, and you're submitting the second job. Then all the jobs are running. And then here, when you're calling result on future 1, as the fit model was done on worker 2, it will return the results almost immediately. And the fit model is already done in worker 3, but the result is saved in the internal executor, in the internal mechanism of the executor. Then you can also call model 2, and when you leave the block, all the resources are cleaned up. So there is one big question that is usually kind of not so easy to answer, is how can you really choose between using thread and processes? And most of the time people answer, okay, threads are running only on one core and nothing, and it's not useful, and you should use processes, but processes has overhead, and Python is not super useful for multi-core computation. And I would say that it's important to know the internal mechanism behind those to be able to make the smart choice between those two. And one mechanism which is really important in choosing between thread and processes is the GIL, the infamous GIL. So what is the Python GIL? The Python GIL is the global interpreter lock, which is protecting concurrent access to Python objects in the interpreter. And actually, only one thread can acquire it. And each time an interpreter wants to access a Python object, either to read it or to write it, so to run Python code, it will need to acquire the GIL. And it's not really designed for efficient multi-core computing. It's designed to simplify the object management and to protect the object management in the Python interpreter. So, as I said, global lock is locked, is acquired every time we access a Python object. It's released, for instance, when we are performing long I/O operations, or by some C libraries such as NumPy or OpenMP that are designed to release the GIL when they are running. So if the library is designed in the right way, when they are running in objects that are, for instance, C objects or C arrays, they doesn't need the GIL anymore, and they release it, and it can help. So now let's see what are the threads. The threads are real system threads that are managed by the OS. So either pthread for a Unix system or Windows thread. And when you use a thread, all the computations are done with a single interpreter. This has many advantages, such as fast spawning, because it's really quick to start a new thread. It's just like a call to the system. It's just a system call, and you just need to implement a really small Python structure, which has really like no memory overhead because it's really small. It's like 100 bytes, I think. Then also, as you're reusing the same interpreter, you're not creating more interpreters, so you don't have a larger memory overhead as you need to reinstantiate some of your variables. And you also have no communication overhead because as all the computation are done in a single interpreter, when you are modifying one object with one thread, the other thread that use the same interpreter will see the same modification. But as there are shared Python objects and a single interpreter, there is only one GIL. And here lies all the problems that you heard about threads, because if there is only one GIL, it means that there is only one thread that can access one Python object at a time. And that's actually what is happening when you're using multiple threads with Python code. So, for instance, here the thread 1 is running, and as it's accessing several different Python objects, it has the GIL which is locked. At some point, there are some there are some regular check. There are some regular check when the Python code is running, and that gives the chance to other threads to acquire the GIL and to process some computation, and that's why you see some changes between the threads that are running. But basically, all the threads are running in a sequential order, and which means that it's not quicker than sequentials. Actually, it was even worse than sequential in Python 2.7, but that was fixed in Python 3. So if you are, as we said, the GIL is released if you are using I/O or C library, and as you see here, for instance, if you are running the thread 1 run with the GIL acquired for a small period of time, and then release the GIL while it's computing some I/O operation, which would give the opportunity for another thread to run at this point. So it means that if you have I/O bound computations, or if the main part of your computations are spent using libraries such as Loki that release the GIL, NumPy, sorry, it would be a very it can be very efficient to use threads because the threads have very low overhead. You have shared Python objects, and so it can be really interesting if most of the time is spent in those blocks where the GIL is released. So either NumPy or I/O or OpenMP and other things like that. If you're not using that, using thread will not be faster than running your computation sequentially. So what about processes? The processes are workers that are created by launching a new Python interpreter. It means that each worker will run in its own interpreter. It has some inconvenience, which are the inverse of what we said for threads. It's slow to span because you need to restart a new interpreter. We will see that slow panning is something that we can maybe manage. It has higher memory overhead because you need to first you need to have a second interpreter. You have to have an interpreter for each worker, and the interpreter takes some memory. I think around like 50 megabytes, 30, yeah. So and also you need to load the libraries in each of your workers. So you will duplicate many things that were not duplicated in threads. Also, you have a higher communication overhead because as you are not using shared Python object, you will need to pass the modification done in one object by one process to the other process. But the main advantage is there is no GIL. There is one GIL per process. Sorry. And so the computation can be done in parallel, even using Python code that does not release the GIL. That's the main advantage. So there is two methods to create a new interpreter. The first one is called fork and spawn, and I will just give you some hints on what is happening. So when you're launching a new interpreter using fork, what you're doing is actually duplicating the current interpreter. So what you just declare a new you just launch a new interpreter that will have the exact same environment as the one in the interpreter you forked. At the time you used the fork primitive. It has some really good advantages, which are that there is a really low spanning overhead because it's almost as efficient as launching a new thread. And the interpreter is warm imported, meaning that all the libraries that you loaded in the previous interpreter are already loaded in your new interpreter. But it has some inconvenience, which is that it has some really bad interaction with multi-threaded program, and it also does not respect the POSIX specification, which are these two inconveniences are pretty much the same. And what is happening, the hint of what is happening is as you're cloning exactly the interpreter, you're also cloning you're also cloning all the Python object that points to thread, to other threads. So if you are using a libraries that relies on thread pools to perform computation, those libraries think that you have thread pools that are started and starts sending some tasks to these thread pools, and the tasks are actually not run, and it causes some crash, which happen for instance with NumPy and using accelerated on OS X, or if you're trying to use OpenMP with multiprocess using fork. The other way to start an interpreter is using spawn. So spawn is creating a new interpreter from scratch. So it has some advantages. The first one is it respects the POSIX convention. And also another advantage is that if you add memory leaks in your main program, those memory leaks won't be also imported in the second program, and you won't have like bad effects. Also, if you don't use some libraries, they won't be loaded in the extra interpreter. The inconvenience is it's slower to start, and also it's first slower to start, but it's also you need to reload all the libraries that were already loaded in the main program. So there is a big overhead to launching this new interpreter. So to sum up a bit the comparison between the methods to launch new workers, the threads are really interesting. When you are running some code that is not using the GIL, but they are not efficient to run a multicore Python-only program. So we are left, if you want to use a CPU-bound Python program, you're left with choosing between a forked process and spawn process, which are more efficient for this usage. You cannot really avoid the communication overhead because you will need to transfer some objects between your processes, between your main program and your processes. So this we cannot do really. And the choice left is either we want something POSIX safe that will run with other libraries, or if we want something really fast to start. And actually, POSIX safe is really important if you try to run some interesting libraries like NumPy for scientific computing. And the question was a bit, is there a way to hide or to improve the spanning overhead? And so that was the start of the Loki project. And the idea was to hide the spanning overhead, so we would be able to use pool of workers using spawn process that would have kind of the advantages of efficient multicore run, and that does not take too long to spawn. And the idea behind that is to be able to reuse the process pool executor. What you will do is there is a big spanning overhead, but you will pay it only once, and once you start it, you will try to reuse the process pool executor as much as possible. So it seems really simple when you think about it. Say, okay, let's just declare one executor and reuse it all the time. The big question is this interpreter robust, and won't I introduce some really hard to debug bugs? So one of the main issue with reusing the process pool executor is that it's not super robust. It's actually quite easy to create a deadlock using process pool executor. For instance, if you submit an unpickable task to the executor, you will have a traceback, but your interpreter will be deadlocked, meaning that it will freeze with no warning, and you won't be able to get it back except by hitting Control C. And when you hit Control C, you will have a stack which is huge, and it's really hard to know where the bug started. It's even worse than that. Even if you don't call the result, you can't even shut down the pool when you discover that it's not pickable. If you try to call the shutdown method, it will actually deadlock and never give you back. You won't be able to run past this point. So what we did was trying to robustify this in Loki by changing a bit the standard library. So if you try to run a task that crash at pickle using the process pool executor from Loki, which is exactly the same API than the concurrent future one, it will actually get the same error with the traceback, and you will have also a user-friendly error that will help you know what happened and avoid freezing your interpreter. We also fixed other deadlocks that are more due to race conditions and that appear a bit randomly. because we think it's really important to have something robust if you want to be able to reuse the pool of workers, because if you do something bad at some part of the code, you don't want your code to crash, I don't know, 1,000 lines later with some unknown error. And we also implemented a reusable process executor. So with the idea of having a global process pool executor. So the idea is that you have a factory function called the get reusable executor. This factory function gives you an executor which can be used exactly like the process pool executor or the thread pool executor that we introduced before. So it can be instantiated with the same parameters, and you can also submit some functions to it and get the results. The function also returns features that you can use easily. And if you call at some other points, you call get reusable executor with the same parameters, it will give you back the one that was previously started. So it really hides the spanning overhead of the overhead of spawning the workers, and when the executor crash after some faulty function submission, if you try to call get reusable executor once again, you will get an executor that is automatically respawn and hides all the management of the executor. So to conclude, one of the main messages of this talk is that thread can be efficient if you have some code that release the GIL. So it's important to try and benchmark the threads pool executor first, because you have no spanning overhead, you avoid duplicating unneedily the Python objects that you're using, and you cannot say that threads are not usable in Python. It's not usable if you are using Python code that does not release the GIL. If your code do not release the GIL, then you should try to use process using spawn, so you avoid breaking the POSIX convention and avoid having some really weird behavior that won't be that will lead to some buggy things happening to your users. For instance, if you want to hide the cost of spawning the processes, you should try to reuse as much as possible the pool of process, and Loki can help you do that. For instance, it's currently under review to be able to be integrated to JobLib to add some better management of a pool of workers in those projects. And thank you for your attention.